Bene, siamo arrivati all'ultima memoria di questa.
Well, we are at the end of the morning with the last paper. Then, after that, you can ask questions to speaker.
Allora, il prossimo ultimo relatore di questa mattina.
The next speaker is Carlo Burkhardt. Sorry for my pronunciation. PhD in metallurgy and material in Birmingham. He's a professor of production technology and director of the Institute for Precious Metal at Fordham University. Lithography-based metal manufacturing of jewelry and watch cases in 316L stainless steel and titanium alloy is the title. The LMM process is described, which is a 3D printing innovative system based on metal powder charged with a photopolymeric binder. It's very good for 316L stainless steel and titanium alloys, which are mainly used in the watch world because they allow high accuracy. You have the floor.
Morning. Thank you very much for the nice introduction, and I'm terribly sorry not to be there. I was hit by COVID on Wednesday evening, so I had to cancel on short notice, and I hope that we can do this online. I also got the difficult task to do a talk just before lunchtime, and I was also given a 20 minutes delay, so I will try to keep it as short as possible. I will talk today about lithography-based metal manufacturing of jewelry and watch cases made from stainless steel and titanium alloys. However, the process we developed is also suitable for precious metals, and we are currently in the development phase of doing so. Because I'm the first time at Vicenza, or would have been, I prepared a little advertising break about the University of Pforzheim and also our institute, but given the time that we have, I will jump over this. It will be in the proceedings. Just a little bit about our institute. We are part of the University of Pforzheim. We are standing on three pillars. One is we are part of the regional precision engineering industry, where we're doing contact research, serial inspection, damage analysis, and so on. And here we have a very nicely fully equipped lab. And we are also, we have two research aspects. One is the recycling of rare earth metals and permanent magnets. That's a bigger one. And the second one is the additive manufacturing of metals. For that, we have a couple of projects with a budget of over 30 million currently. And we are nicely equipped also for the additive manufacturing to cover the whole process chains. And in that circumstance, or in that framework, we developed a completely new additive manufacturing process, which is based on lithography. And Dr. Klotz already said that with laser powder bed fusion, there are a couple of issues that have to be solved. One is the heat dissipation. The second is that you always need support structures, which have to be removed afterwards. That during the very inconsistent heat distribution, you're very hot where the laser is, but should be cold where the powder is. That's not to be fused. You also have thermal stresses, and this also leads to a lot of after treatment and rework that has to be done. And the process we developed is based on avoiding all these issues. It's based on vat polymerization. Most of you will know it as stereolithography. I come to that, why it's working to make metals with stereolithography. But the outcome is that we have very good surface characteristics. So far, we don't see any method that is as good with that. We have a very good geometrical precision. We have no thermal distortions in the material. Currently, we work with stainless steel, with tool steels and titanium, but as I said, we are currently working or starting also with precious metals. The whole procedure is also suitable for non-weldable material, which is important if you want to do material mixtures. The printing speed is about 16 cubic centimeters per hour. That's not very much for industrial purposes for large scale, but it's very interesting for small scale and also what we think for the jewelry production. There's one big difference compared to laser sintering. It's only suitable for small and very small parts. Currently, the rule of thumb is around 30 grams, but that's, of course, depending on your material. 30 grams of titanium are obviously much bigger than 30 grams of gold. And it's suitable for small and moderate quantities. How is it working? It's not as laser powder bed fusion a direct process where you get directly your part when you print it, but it's a so-called indirect or sinter-based process where you first print the green part and then remove the plastics. So you start with the CAD or scan data. You do the printing, and then we have a special procedure which I show you in a bit, which is the unmolding and the cleaning of the part. Then you get a green compact, which goes into the sintering furnace, goes through a certain shrinkage, and then you have your LMM part, or lithography-based metal manufacturing part, because that's such a monstrous word, we call it LMM. So the machine itself looks like you see on the slide, and the material is a very special sauce, we call it. It's a mixture of metal powder and a photopolymer, and the metal filling ratio is between 55 and 60% of weight percent of material. The consistency of the whole material is best compared to butter, which means at room temperature, it's solid. If you cool it down, which we do in a printing chamber, it's nearly hard, as it would be a very cool butter block. But if you heat it up over 50 degrees, it gets a very low viscosities, and it's really water-like. And this helps us to apply the material. So what you do, you have a feedstock reservoir, which you see here. I don't know if you see my mouse pointer. I'm painting on it. If you don't see it, the feedstock reservoir is written here. There, the material is deposited. Then we have a heated wiper blade, which is heated up to 80 degrees, which liquefies the material, and then you can make a very fine layer of this slurry, of this mixture of the polymer and the metal. And then in your print chamber on the build platform, you expose the whole thing with UV light, with a DLP projector from above, and then the material hardens where it's struck by light. Once you have exposed one layer, you go down one and do the next one. And the result is a green compact, which is embedded fully in this building material mass. So that's a representation. Material is taken from this reservoir. It's put on the build platform, which was in red. Then it's exposed with ultraviolet light. It's hardening. And once this is finished, and it's real time what you see here, that takes quite a while, the next layer is applied again, and the procedure starts once more. So in the initializing phase, which you see on the picture of the left, you have a very clear, a very smooth surface because it's liquid and because it's water-like in its melted state. You don't have any kind of printing lines or scratches in the surface. And then you expose the whole thing here again, a video representation. So this coater puts a new layer of the material on top of the build platform. Then the DLP projector will expose the material. In this case, you will see two watch dials, which are done. And because you're exposing always the same surface, you can expose one layer with multiple materials at the same time, which makes the printing quite efficient. And this means, despite we have such a small build chamber currently, which is about the double size of a business card, you have a highly efficient printing process because you can use that build space really in a maximum, because almost any arrangement of identical or different parts in the build space is possible because there are no support structures required. Due to this consistency of the material, this butter-like structure, It's supporting the parts that are directly below. So as you can see, you can make multiple layers of different parts or of the same parts at the same time. So once your print job is finished, which can take a couple of hours, usually we do this overnight, you remove this material block. And again, I think the analogy of a butter block is quite nice because it's a solid block. You put it on a net, which you see in the middle, put it in an oven at 80 degrees. Then the non-exposed material liquefies, and the exposed samples, the green parts, which are solidified, they remain on the net. The other material you can directly reduce, but you have to mix it again because there are certain tendencies to demixing. So it's mixed again, but in general, there's no material loss at all, apart from what's remaining on that net and what's remaining on the surface. And you see the surface is kind of slurry-like. So what we do, we put in ultrasonic baths with some special cleaning agent for a couple of minutes, and then you have your green parts. These green parts, and then it's why it's called sinter-based additive manufacturing, is going into a sinter furnace. And first we do a thermal debinding. This is usually done under protective atmosphere, which could be argon, helium. No, not helium. It could be argon, nitrogen, or hydrogen. Helium would be far too expensive. It would work, but that's kind of pointless. Then around 300 degrees, you remove that residual binder. You basically burn it. And then because of the thermal expansion, your powder particles, they get into contact because of the high surface energy. When heating further up, they build sintering bridges, and in the end, they build a fully dense microstructure. And that's a procedure that's completely well known from metal injection molding. So basically, the process is like injection molding, metal injection molding, but instead of making your green part with an injection molding machine, you print your green part with this newly developed printer. We sinter in a retort furnace. As said, the debinding and the sintering is a combined procedure, so the parts are not removed in between. We can go up to 1450 degrees here, which means that the most materials could be sintered that way, and the sintering temperature is about 80% of the melt temperature. But that's just a rough rule of thumb. Of course, this has to be optimized to the process and the parts. So you have your 3D data, but because of the removal of this residual binder, you have a shrinkage. And this shrinkage I put down here with roughly 20%. Of course, we know it to the last digit, so 3 digits after the comma. We exactly know the shrinking factor, but this is depending on the material used and the filling ratio. But for each of the feedstock composition, we know the exact shrinking ratio. And because it's a 3-dimensional shrinkage that's the same in all 3 directions. It's very simple. So you blow up your CAD data by the shrinking factor. That in the end you get your final part. So you compensate for that shrinkage. As I said, the parts are very precise. In the finished parts, tolerances of up to 0.5% of nominal dimensions are possible. So we're really in the 1/10 or 100ths range, depending on the dimensions. But you still have a staircase effect due to the layer-by-layer production. That sometimes when people look at the parts, what they forget, but you see it here on this scanned part, it's still kind of staircase approximation of the real geometry. And this can be, especially in jewelry parts, this can be not so nice if you make very large radii, because a very large radius means that you probably have 2 or 3 steps which then are seen as shrinking lines on the surface. So you need a certain kind of strategy to print your parts with very sharp edges, for example, or to do some rework afterwards. The surfaces, as I said, are the best one we currently see in the market. So as sintered, means as printed and sintered, we have a surface RA of about 7.5 micron. You see on the right side a profile measurement, what you see. And if you look at it with a very high magnification, you really see the printing pixels. So currently we are using a 4K projector, but we're now going to higher resolutions. So this will get better over time. If you sandblast the material, you can go down to 2.8 micrometers. And if you tumble polish, you can get RAs of 0.03 or RZ of 1.5. All the parts that I show now are not polished by hand. It's all done in machine processes. And again, as we don't have any support structures, that the afterwork really and the rework can be minimized very much. So here's some parts. What you see on the left side, that's the watch case. And this watch case is as printed. So you see here the printing lines on the surface, but this designer, he said he wants to have this special appearance just to feature the printing process. On the right side, you see a flat part. This has a golden appearance, and that's because it's electroplated. So that's a stainless steel part. So we cheated here a bit. Yeah, and you see here on the surface, this is not treated at all. You see the kind of pixel structures. In this watch, the indicators here are also printed 3D, and you see that you even can, this is one centimeter here just for, to give you an idea of the size. How small these parts are. You see the printing lines, yes, but you also can read what you see on the surface of it. On the right side, you see a ring, as printed, only tumble polished. Here, this part looks very interesting, very nice if you have a first look on it, but the thing is a reject part, and I chose it for two reasons. Because you see, first of all, that very delicate structures can be printed. And secondly, you see that this part has not been cleaned properly. So here with the ultrasonic bath, we didn't get out all the not exposed printing material. And if you don't do that, it will sinter together with the rest. So this should have been cleaned better, and this could have been done with a kind of airbrush gun with a very mild spray of material. So the second part that was made was cleaned here much better. Again, you see some printing lines, and this is because the whole thing has an oval shape, a very large radius over it. So this has to be after treated with some hand polishing. As I said, I'm showing pictures here not that have been treated afterwards. So on the right side, a little gimmick here for a trade exhibition. These are some structures just to show what is possible with the process. Here, printed parts, sinter parts on the right side. For scale, you always see either the matchstick or here, this is 1 centimeter. So you see a very, very detailed process, which gives you fine structures. And yeah, the disappointing thing is that the pictures look much worse than the real parts, because the resolution of the cameras is better than your eye. So I would really have liked to come there and have a box of these materials with me to give you a real representation. You can make fully functional part, though this ring with this chain here was printed in one bit, and after sintering the parts, they will stick together a bit. But they are not synced together, so with a little bit of mechanical pressing and pushing, you can make it fully operable, that you have then a stainless steel chain that has really no connections, and nice gimmick. This watch case you've seen before, and again you see that a very, very high detailed resolution is possible. You see the matchstick here for comparison. Here on the left side, a representation of this ball, which has inner structures. And because of the shrinkage of the material, one can also imagine that it could work together with some inlays that one puts in. The restriction obviously is here that it has to go through the sintering furnace. So if you put in, for example, a precious stone, it has to be temperature resistant to the sintering. On the left side, part only tumble polished. So you see that the surface is really very good and also allows glossy structures. If it would be hand polished, even more. And then on nearly the final slide, this brooch we've made for the Jewelry Museum of Pforzheim. It's actually a copy of an existing part. So what we've done with a scanning machine, with a gum scan, we took the geometry, we printed the part, then it was electroplated with gold, and then it was hand painted with some cold animal or animal paint. On the right side, always the same part. Here, on the left side, electroplated with gold. All the others are PVD coated in different colors. And just for a comparison, a DMLS part that has been reworked for 3 hours. And you see here where the support structures have been to support the material. On the right side, the same watch case as printed and fitted into the watch case. Because we think that this process is very interesting for industry, and not only for the jewelry industry, but as Dr. Klotz said before, and Dr. Bulling also for medical purposes, for aerospace and so on. We made a spin-off at the university in April 2019, which is funded by the Young Innovators Program of the Ministry of Science, Research and Arts in Baden-Württemberg. And this spin-off is specialized in this LMM procedure and related development. So what they're doing, they're conducting feasibility studies for components and materials, which means you could come to them if you have a design idea, and they would make you 1 or 2 or 5 parts to see if it's feasible, if the geometry is suitable for LMM. They also make small-scale production, so a couple of 100 parts per year, or also a couple of 1,000 parts in some cases are possible. And if your business, your ideas would explode, which would need higher quantities, they are also installing the whole process chains for in-house production. And the process chain means the printer, plus the cleaning devices, plus the sintering furnace, including the parameters that a production can be set up in-house. So that would bring me to the last slide, and I was really talking here in off. I have no idea if you heard me. I have no idea if you've seen my slides. I hope you did so. And if you have questions, here's my address. I'm happy to answer your question at any time if you come back to me. Thank you very much.